Welcome to the June 5th, 2017 Kubernetes SIG Apps. And I'll get started by sharing the agenda we have for this week into chat. So in chat, you just got a link to the agenda that we'll be going over this week. We have some announcements, a demo, and then some discussion. I'm Matt Farina, and so I'll kind of be guiding it through things this week. And so I'll jump right into the announcements. The first one we have is kind of a question, or we're looking for folks who are interested in Monocular. For those of you who aren't familiar, Monocular is a project that kind of gives you like an app store for Kubernetes. It has the Helm charts listed, and then you can go find them, read through the details, and even if you set it up in your own cluster, you can have things like an install button. I just dropped a link. Yep, thanks for Adnan for dropping the link to it in. It's actually what powers kubeapps.com and lets you go through that. But if you're running it in your own cluster, you get some more capabilities. We're looking into things such as what's the roadmap going to look like? Where's it going to go? Some of those features. Does somebody want to contribute to some of it? Do they have suggestions they'd like to get into the backlog? So if you are interested, please speak up, email Adnan, and let's get involved. This looks like an interesting project because it actually takes the technical command line stuff and puts a nice interactive interface on it, which for a lot of people is something that's needed and useful. That's the first one. And then the second one we have is, is anyone able to demo their 1.7 feature at SIG PM meeting tomorrow morning, which is 8:30 to 9:30 Pacific Standard Time. We have been allocated 3 slots, estimating roughly 5.
Oh, hello. Oh, okay. Yeah, hello. Sorry. Actually, this is Dan. So I think I cut out for a minute there. But I think one of the announcements that I had written there was about doing some demos at the SIG Apps meeting tomorrow. So it's any 1.7 feature, whether it's alpha or beta. If anyone's ready with features, we can demo them tomorrow. So let me know, and I'll get you added to the docket over there as well.
And so people should reach out to you if they are if they're interested.
Yeah. I mean, they can tell me now, or they can also just email me, and I'll make sure that they're on the agenda. But it's really the only day that we've been allocated at the SIG PM meeting. So it's really a way that we can showcase what we've done for 1.7 to the other PM reps there, just to make sure that other people are aware, as well as if we need anything, we can also do that too. But it's really primarily the point is for us to show the rest of the community at large sort of what we've been building for 1.7. So if there are any features that are ready, then yeah, I can add that to the agenda in tomorrow's SIG PM meeting.
Fantastic, thank you. So if somebody's interested, please reach out and let them know.
Thank you.
And so the next thing we have on the agenda today is a demo of the app controller flows demo and some QA time. Stan, are you on?
Yeah, hello.
All right.
Do you hear me?
We can hear you. The floor is yours.
Thank you very much. So let me share my screen.
And I can see your screen.
Excellent. So hello, my name is Stan Lagoon. I'm from Kubernetes. I'd like to do a little presentation of features that recently landed the app controller, and which is called flows. I guess most of you are familiar with app controller to some extent. Actually, it's very easy to be familiar with it, since it is, or should I say it was, very simple. All it has is resource definitions and dependencies between them. So you just define dependency graph out of them and let app controller deploy everything in the order specified by the graph. Here's how dependency graph may look like. And if you take a look at examples that come with app controller, they all have dependency graph that look more or less like this. The problem is that in real life it looks more like this one, the one on this slide. And once you get to graph like this, it becomes extremely hard to manage it, do changes, or simply understand what's going on there. Here's when flows come into play. Now this graph may look like a mess of colorful boxes, but they actually do mean something. The complexity comes from the fact that we deploy systems that are made of many applications, and each application by itself contains of some Kubernetes resources. If we make dependency graph out of resources from each application, we get a mess like this. But if we could redefine the graph in terms of applications and write dedicated graphs for each of them, it becomes much easier to understand and manage. Flows do just that. Flows is yet another graph vertex that you can use in dependency graph to represent another graph. Not only it abstracts individual pieces of graph, but also break dependencies between resources of different applications. Since flow graphs are all separate graphs, it becomes possible to do changes to one system component without affecting others. In other words, flow is like a black box that encapsulates its resources, so that you can change implementation of one flow without breaking others. Flow can be run by users with help of app controller CLI, or they can be run from each other, which means that one flow can consume other flows. And then we can compose flows into bigger flows. So what can we do with the flows? We can define applications with them. Moreover, we can also define entities those applications consist of. For example, it can be a database cluster node, so that we could compose database application from node flows. We can even have flows that represent lifecycle management operation to be performed on an application. But in order to do it, the flows must be reusable. The most important piece of functionality that turns flows into reusable building blocks is the ability to have parameters. Parameter value may be used inside the resource definition with $syntax, as shown on this slide. So now instead of having separate graph for each of the application nodes, we can have just one parameterized flow with all the data that is not specifically extracted into parameters. Parameter value may come either from CLI or passed from another flow for case when flow is consumed by another flow. The second principal piece of functionality is replication. With parameterization, we have a generic flow for a cluster node. But how do we build systems that consist of variable number of nodes? Replication does just that. When user runs a flow, he can specify a replica count number. App controller will automatically do this number of graph clones, each with a unique name, and pass this name in special parameter called AC name. If this variable is used somewhere in the resource name, then each flow replica will get its own resource. If it isn't, then the resource will be shared between all replicas. Not just that it's possible to specify a fixed replica count, but also can be relative. So one can say, create me one more replica, or delete two last replicas. This makes it possible to implement upscaling and downscaling of the application with just one flow. For downscaling, it's even possible to specify actions that need to be performed before a replica gets deleted. For example, it can be unregistered node from the cluster. Now I'd like to touch a TCD example, which is a good demonstration of what can be done with flows. The goal was to create applications that is highly available and scalable, and all operations can be performed by app controller alone, without additional operators. As a result, the TCD application can be deployed, scaled up, down, and healed by running some flows. Also, it has monitoring job, which periodically queries TCD cluster health, and if it finds a healthy node, it automatically runs flow which recovers it. Now that TCD is an example of multi-node application which cannot be reduced to just a replication pod. For example, initial configuration requires that each node know all other nodes, and thus in two-node cluster has different configuration from three-node cluster. So you cannot just take one spec and deploy several copies of it. Another problem is that there should be a service for each of the nodes, so there's a need to replicate a set of resources rather than just pod. The TCD application consists of three flows. One that deploys initial cluster, flow to scale cluster, up and down, and flow to recover unhealthy node. Let me very briefly walk you through them. The first one is TCP Bootstrap, which deploys initial cluster. On the left of this slide, you can see how the flow looks like, and on the right, what it turns into after replication. You see here that there's service for each of the pods, and all services deployed before pods. The script in pod definition uses kubectl utility to get list of services, and this is how it knows all the nodes that are going to be in the cluster. And then the monitoring job is started only after all pods are created. Thus, cluster of any number of nodes can be created with just one CLI command. Then there's a flow which can add or remove nodes to a cluster. It starts with job that registers new node in existing cluster, gets new cluster configuration and puts into config map. So when the pod starts, it has all the information and already registered in etcd. And the last flow is the etcd recover flow, which removes unhealthy node from the cluster and creates new node instead. The removal is performed by the job that's also used for downscaling. And then the flow calls etcd scale to create new node in place of the one that was deleted. So here's an example of how one flow can consume another flow. So I don't know if we have time left, because I wanted to show how it works so that you see it's not just presentation. I suggest let us start with Q&A, and then I'm going to real life demo.
Okay.
Like, I know it was very fast. So no questions?
Anyone have questions? All right, we can go. I guess we'll go into the live demo.
Right, just in case if you have some questions later, I'm going to share this presentation. There's link to documentation and also link to a pre-recorded demo, especially for this TCD application. All right, so do you see the text here? If it's big enough?
Seems big enough to me, at least.
Yeah, it's fine.
All right. So the first thing I'm going to do is upload definitions to Kubernetes. I have a very simple script that does that. So just calls kubectl upload. So now I'm going to create initial etcd configuration. And this is how I run flow. So this is kubectl run etcd bootstrap flow name. And I want to have cluster of, I don't know, let's say 3 nodes. So I specify a replica count, which can be any number. It generated the graph, and you can see like deployment was very fast. So if you see what was deployed, there are 3 initial pods. There is a monitoring job, service for each of the nodes, and 1 service per application. Yeah. So for example, we can see that TCD works by just saying kubectl exec see 3 nodes are running. And now I can use another flow to upscale it. So instead of bootstrap, I say cd scale, And for example, +2 replicas. Note that it creates replicas one by one, because in TCD you cannot create all replicas in once. Like, nodes need to be added one by one. So now it's 5 pods, 3 initial, and 2 pods were added. So it's 5 nodes now. And I can also, for example, make it 4. So instead of +2, I say -1. So now it's 4 nodes running, and you can see it's done by just one CLI command. No, I can delete any of the nodes or delete nodes of Kubernetes itself, and it will automatically recover with yet another flow, which is normally not called manually, but it's called from monitoring job. I can probably show you YAML definitions of the flows, but
Please.
I'm not sure. So you don't want. All right. So this is a TCD example. So everything we have here is like normal resources, loads, services, and so on. The only new resource that was added is flows. So it's very simple resource which define basic properties of flows. In alpha namespace, kind flow name. Exported means that it can be run from CLI, otherwise it can only be consumed by another flow. Construction and destruction are labels, selector for dependency labels. So this is how we know which resource belongs to which flow, by filtering dependencies by these labels. Construction is what normally created when I deploy something, and destruction is what happens when I remove replicas. So when I deleted the TCD node, it executed dependencies marked with this label. A replica set is like common namespace for replicas shared between different flows. Here we have 3 flows, and we have Bootstrap flow, which creates initial configuration scale that scales up and down, but I can remove nodes created by Bootstrap flow with scale flow. So like they share replicas. And parameters, just declaration of what parameters can be accepted by the flow. So here we have 2 parameters, and both of them have default value, which means they're not mandatory. So I can, with CLI, I can pass cluster name. By default, it's TCD, but I can pass different name. Now this is useful, and if I want to have several TCD clusters in one namespace, so they don't conflict, I need to give them different names. And liveness probe interval is how often monitoring job checks for unhealthy nodes. This is Bootstrap flow. Scale flow, like very similar, just different labels. There's only one parameter, and it's sequential, which means replicas are deployed one by one because I cannot add more than one node at a time. Recover flow. So nothing magical here. And here how dependencies look like. So this is dependency between graph node, which you probably are familiar with. What was added here is ability to pass arguments between nodes in the graph. So, for example, here we use job with parameterized part in its name, and we pass this parameter from inputs of the flow. And in order for dependencies to match against flows, now most of dependencies have labels which match what was in the flow definition. So it's really, really simple. I wish there was some UI for that. We used to have one, but it's now a little bit outdated. But it has big advantage over operators that it's just Kubernetes resources. You don't need to do any programming. Just set of resources and dependencies between them. That's it. But with parameterization and replication, there are now a lot of things that can be done with subcontroller, which were impossible to do before. And this example, it's really good because configuration which it generates, like it's very dynamic. If you try to do it manually, you will need to do a lot of things. Like if you want to add another node, you need to change existing resources and a lot of manual stuff. And if you take a look at TCD, like TCD example on which it based from CoreOS guys, it's very, very simple, especially on scale. If you need to have a TCD of 11 nodes, you definitely don't want to do it manually. Right, so that's it for me. Like, if there are some questions, I'll be more than happy to answer. Anybody?
It noticed, so one of the comments from chat is, it looks like you specify the edges twice. A parent nominates its children and each child nominates its parents. Is that right? Or its parent?
Now, each dependency have its parent and child. So if you draw a graph, dependency is arrow between two nodes, and each arrow have its parent and child. Like it's for each dependency, it's specified independently.
Okay. Somebody else asked, could you comment on the variables that are passed between the parent and children? For example, where do they come from?
So usually they came from flow arguments. So if you take a look at flow, here's Bootstrap flow. It has two parameters, cluster name and liveness probe interval, and they are declared here. And then when you define dependencies, so for example, AC name is special variable which is replica name. It's provided by the app controller itself. But other variables, they come from flow inputs.
Are the variables that are provided by app controller documented somewhere?
Yes, it's only few of them. It's AC name and I guess one or two more, like flow name. So here how they used. See that AC name is part of resource name. When app controller deploys this resource, it just puts real replica name here for each of replicas. And because each replica is given unique name, you get unique pod name for each of the replicas. App controller has list of places where it can replace variable names. For example, it doesn't do this in bash scripts. That's why I put all my variables into environment and then use environment variables in bash script. There's only a few predefined variables which are documented, and they all start with AC underscore. Everything else comes from flow arguments.
Okay, thank you. Does anybody have any other questions? Going once, going twice. Thank you for a great demo and walking us through not just the code and showing it to us, but how it works. Thank you. And so the next thing we have on the agenda is a discussion, and our discussion topic is the Snapshot Proposal and how end users could use this feature for their stateful applications. Do we have anybody on to talk about that? Do we have anyone on who can lead that? Ooh. It sounds like the person who wanted to have the discussion topic may not be here today. Does anybody else capable of discussing this particular topic?
I can give you some general information about it. I mean, I can't go into depth in the implementation, but the basic idea is that you would be creating via the cloud provider storage snapshots of PD or EBS that map to persistent volumes. It's actually a really intricate proposal in terms of how it would work, but you'd also be able to rebind. Like, so if you created a stateful set with the persistent volume claim, you'd be able to map the persistent volume claim to a previously taken snapshot and bootstrap your stateful application off of basically off of a previously restored snapshot. And I think the primary use case that it probably will help people with in terms of a data availability plan is not so much disaster recovery, because with EBS and PD, you know, with cloud storage solutions, it's not like back in the day when primarily you were building stuff on top of a cheap array of commodity storage. The chance of disk failure is much lower. But if somebody fat fingers and drops all your tables, if you've been taking incremental snapshots on a regular basis, you could do a point-in-time restore for your storage application back to the snapshotted volumes. It looks pretty cool, but it's not at a state where I've had a chance to play with it at all. So,
no, that sounds really useful, because the ability to, oops, we screwed something up, to restore from that quickly, that's important.
it is, but honestly, from my perspective, and most of the stateful applications that I've used in production environments, they provide some level of application level snapshotting feature. Like, for instance, with Cassandra, you can take incremental snapshots and upload those the hard links to the sorted string tables up to a cloud storage provider. You can do the same thing with Elasticsearch. It provides default snapshotting features. Actually, those will go directly to GCP or, well, to any S3 compliant storage array. So, and a lot of times if you use the application level, you're going to be in a better state than if you were just snapshotting the block device. The other thing that I don't really understand how they're going to solve very well is you're going to have to lift writes and fsyncs off in order to get a consistent block storage snapshot. So I don't know how you would do the point-in-time snapshot on a running application unless you lift all the write pressure off of it. A lot of the application level snapshots that are provided as functionality for storage applications come with a baked-in solution to allow you to continue to take writes and get an eventually consistent snapshot. So I don't know if this solves that problem.
Okay. Sounds like we've got some questions. We might want to reschedule this one then. Somebody asked the question, it says, you mentioned EDs. Is that empty directories? Was that EDs or EBs?
EBS, embedded block storage, and PD, yep. Persistent disk.
Yeah, okay, that's what I thought. All right, then I'll actually see about getting this one rescheduled for a different time. Since we have 27 minutes remaining, did somebody have something else they wanted to talk? We'll consider this open floor time, open discussion time. Does anybody have anything else they'd like to bring up and discuss? Going once.
Just that, hey guys, this is Scott Rigby. Just that Core OS Fest was really great. Thanks to everybody who made it awesome, and also to the Charts Hack Night. That was really just fantastic. It's not really a discussion, it's more like a comment, since there was nothing else happening.
Thanks for pointing it out. Yes. And it seems Matt Butcher agrees with you. So, good. And I'm sure he loved the idea of a Charts Hack Night with the whole hum relationship.
Yeah.
Somebody's asking if there's a link to the Snapshot Proposal. Does anybody have that they can share? We can add it to the agenda.
I can find it and add it to the agenda after the fact.
That would be great. Thank you. All right. Well, if we don't have anything else, then we will give everybody 25 minutes back of their time, and we'll reschedule this one. Thanks, everyone, for coming, and have a wonderful rest of your day.
Thank you.